So we are very happy to introduce Jayadev Athreya, our own Jayadev from the University of Washington, who'll be talking today about counting tripods on the torus. Take it away.
Great. Thank you guys for giving me this opportunity. Hopefully the pre-talk was fun. It was, I wanted to make that as elementary as possible, and I want to make this talk also as self-contained as possible. So let me just go back to let me state the universe that we're going to be living in this whole time. So the plan is to state the universe that we're going to be living in, talk a little bit about what we're going to be counting, and then how we count it. And I should mention all of this is very much work in progress, in the sense that we're hoping that the story that we tell you for the torus is going to be true for lots, or is going to have analogs for some of those other objects that I described for you at the end of the intro talk, namely higher order differentials. And I should also mention that what I'm doing is joint work in progress. This all started at MSRI with, let's see if I can get the names in order. David Alessino, Vincent Delacroix, and Andy Knightsky. Okay. And I should also say that some of the motivation from this comes from something called spectral networks, which arise in some problems at the intersection of mathematics and physics. I'm not going to have a ton of time to talk about that. Probably I want to focus on the concrete problem, but I would love to talk more. I'm not an expert by any means on spectral networks. Actually, I think we have some people in the audience. Tom Sutherland might be a good person to ask about spectral networks as well. But basically, for this audience, a very brief description is there are certain types of graphs embedded in surfaces with or immersed in surfaces with certain geometric structures. And what I'm about to describe is a counting problem associated to counting certain types of immersions of graphs on a surface with a certain geometric structure. And so therefore, it's kind of a toy model problem for this. Okay, enough with the generalities. What's the problem we're actually studying? So the universe is the torus. Oh, sorry, Zoom things. The universe is the torus. And the torus, the square, good old square torus, I'm going to think about it. I'm going to be using a lot of complex notation. So I'm going to be thinking about it as C modulo Z adjoined I. So this is the square torus. Okay. Here's a picture. Maybe this is 1 and this is I. And then so this is, you glue opposite sides of this and you get an actual torus. Okay. What are we going to count? So in the pre-talk, we talked about counting, we talked about marking the special point, which we call 0, which really is, it's special in this sense in that it's, the torus is also an abelian group, and this is the identity element in the abelian group. So it's a special point. So let's go ahead and mark that special point. And in the pre-talk, we talked about saying, oh, what are trajectories that start and end at that point? So for instance, maybe you go halfway here, there's a trajectory that starts and ends in that. But I want to think about this trajectory in a slightly different way. I want to think about it as maybe I take some point in the middle of this trajectory, I shoot out 2 trajectories at equally spaced angles, in this case 180 degrees, and as I shoot out, oh, did the blue lines not show up? Huh. Can you, okay. What I'm writing is not
they're just a bit delayed. So they're appearing a few seconds after
things are just a bit delayed. Okay, things are just a bit delayed. Okay. So I take this blue point, I shoot out lines in both directions, right? At equally spaced directions in angle, right? So there's 360 degrees worth of angle, and I pick a direction, I shoot something out, and I shoot something out 180, and I end up at singular point, at the special point as I go in both directions. Okay, so this is kind of, we can think of closed geodesic passing through 0 as a regular point. So non-zero point, so regular just means non-zero in this case, together with trajectories at 180 degrees from each other, or pi, angle of pi, shot out from there shot out, both ending at 0. Okay. Does that make sense? Of course, there's a lot of ambiguity over the choice of the point. I could have picked any sort of interior point on this pink interval and done that. But it makes sense to shoot out things at equally spaced angles, 2 equally spaced angles, and then we're going to see what we get. Okay, but that's 2 equally spaced angles. Why not 3? So what do I mean? Why not try and find a tripod? So this is going to be the intuitive definition of a tripod. So a tripod is going to be a regular point. So that is a non-zero point P in my torus, together with 3 trajectories, straight line trajectories, emanating from P, which each end in 0 at angle 2 pi over 3 from each other. Sorry, I'm running off the bottom of the page here. So maybe I'll start on the new page here by just drawing you a picture. So what do I mean? Actually, let me show you a picture of such a thing. Hopefully the delay actually happens. Okay. Here's a picture. You can ignore the other auxiliary things for right now. Think about, there's my regular point P. And these are I shoot out 3 trajectories at angle, they're all equally spaced in angle. They're at angle 2 pi over 3 from each other. And each of them hits a 0. So this is what I call a tripod. Now, I'm not going to emphasize, I'm not going to insist that this thing be embedded. I'm going to allow things to intersect itself. So for instance, if I make A to B, so now this is another example of a tripod where I shoot out trajectories 120 degrees. 2 of them go straight to the 0. The other one kind of does a little bit of wrapping, but it comes to the 0. Notice this one does cross itself. So maybe I will hide some of these other lines. Well, so the lines involved in the tripod are the purple one, this kind of red one, and this orange one. And then here, maybe I can draw you another one here. Maybe I'll do, there's a slightly crazier looking tripod. Oh, it's missing. Sorry, this is I think I broke Desmos. Yeah, there's a slightly crazier looking one. Again, these guys are all, this one should be emanating backwards 120 degrees. That's a Desmos artifact. So let me actually pick one that looks a little bit better. Let's do 1, 1. Where did P go? Oops. You know what? We're just going to stick with this guy. 0, 1, and we can do, let's say, there we go. That's a fun one. So this is another tripod, and it's again kind of wrapping around a bunch of times and crossing itself. Sorry, you guys can't. I realize you're about 3 seconds behind me. There we go. This is a good one. This is another tripod on the torus. This is just drawing it on the torus. It's wrapping around like this. So I'm going to write down a formal definition, but are there questions about what a tripod is at this point as I write down a formal definition? Sorry, the AirPlay is really not doing a good job. I have to work on this. Maybe everybody happy with the definition of a tripod? Okay, so let me give you a formal definition. A tripod on the torus is the following. So is an isometrically immersed copy of a metric graph G of T1, T2, T3. What's G of T1, T2, T3? G is not just a metric graph, it's a metric graph sitting inside of the plane. So what's G of T1, T2, T3? G of T1, T2, T3 is the following graph. You draw the line, so TIs are all positive numbers. So you start at 0, you go out to T1, you go out to T2 e to the 2 pi I over 3, and you go to T3 e to the 4 pi I over 3. So this is a picture in the plane. So it's really this. So it's really a pair, sort of G of T1, T2, T3, together with a map. Let's call it I, or maybe not with that weird arrow over I, where I of the point 0. So I maps. Sorry. This definition takes a little bit of time to write down. I maps G, I'm going to drop the TIs, to the torus C mod Z adjoined I is an isometric immersion with I of 0 is not equal to 0. We want the center point of the tripod to be a regular point, and I of T1 is equal to I of T2 e to the 2 pi I over 3 is equal to I of T3 e to the 4 pi I over 3. All of those are actually equal to 0. The length of the tripod is just T1 plus T2 plus T3. And so you've seen, I've showed you some pictures of tripods in the previous thing, and we'll see some more. So, but the counting, and we say, by the way, we say a tripod is primitive if it is not a scaled copy of another tripod. I don't want to go too much into this definition, but maybe showing you a picture will actually be useful here. Here in Desmos here, I've shown you, okay, so maybe this is a tripod associated, this is a very simple tripod associated to, you know, if I take a triangle, oh, you can't see it yet. Right, so if you take the integer vectors 1, 0, and 0, 1, you can kind of inscribe this tripod inside of it. But I could also do 2, 0, and 0, 2, and that tripod would just be just a scaling of the original tripod, right? I would just be wrapping around the same stuff. Sorry, this should be. It would just be wrapping around the same things kind of twice, and so that's not genuinely a different tripod. Okay. Oh, sorry, I had this problems when I was teaching as well. This GoodNotes has been giving me a lot of problems with this talks. So here is, let me state the problem. Let me state now the problem, and then let me state the result. So the problem is, question, let's let n of R be the number of primitive tripods of length less than or equal to R. So what is the asymptotics of n of R? asymptotic behavior. So here's the theorem, which I really like because it has pretty numbers in it. N of R, and remember this means that the ratio goes to 1 as R goes to infinity. This script, this tilde with an underline on it. Okay, is like 1 over zeta of 4 square root of 3 over pi, square root of 3 times pi over 24 r to the power 4. In other words, if you do some arithmetic, it's 15 square root of 3 over 4 pi cubed times r to the power 4. That is the asymptotic behavior of this. Okay, before I launch into a little bit about how you prove this, I'd like to ask if there are questions about the statement of the theorem. Okay. Great. So what we're going to do is the proof is going to be we're going to turn this into a lattice point counting problem in R4 or in Z4 if you prefer. Okay, we're going to try and count. We're going to count pairs of integer vectors, or rather integer vectors in Z4. Okay. So here's the first key observation. Lift the tripod to C. So we take the tripod on the torus and we think about it now as lifted to the complex plane. So what does it look like up in the complex plane? Well, we can always make one of the endpoints. One of the endpoints can be moved to 0. Others will be integer vectors. Will be z, w. Both of those have to be Gaussian integers, right? My tripod ends at 0 on the torus, so therefore, it's going to have to look something like this upstairs, right? So here maybe is, maybe this is 1 and that's 2, and maybe this is this is 2 plus I here. So maybe there is one side and maybe another side is, so this is I, and maybe this is, and this is, let's say 1 plus, oh, that's not 1, sorry, that's a half. That's 1. Maybe that's 1 plus 2I, and those are my endpoints of my tripod, and my tripod in here looks something like, maybe my tripod point is here, and my tripod looks something like that. I mean, I'm not guaranteeing you that that's a tripod, but that's basically what I'm trying to draw, is basically trying to draw the tripod inscribed inside of this triangle. Okay. So you lift up, maybe this is just an example of what it could look like. So this is, some z and some w. So the question is, how do I build, so suppose you gave me some z and w, which are integer points. Is there always like a tripod that's inscribed inside this triangle, 0zw? If so, how do I find it? What's the, and then if a pair, can I write down conditions for a pair of integer vectors z and w to have a tripod or to not have a tripod inscribed in a triangle? Okay, so here's a little digression. Steiner trees. So hopefully some combinatorialists in the audience will perk up, because this is a phrase that I think combinatorialists, and especially people working combinatorial optimization have heard a lot. Is this phrase called a Steiner tree? Here's a very simple Euclidean geometry problem. Given 3 points in the plane, maybe let's call them 0, ZW, just to be suggestive. You can always have one of the points. Find P in the plane such that the quantity Z minus P plus W minus P plus P is minimized. So this turns out, so here's a beautiful, beautiful exercise in Euclidean geometry. It's not a trivial exercise, it's quite difficult. So here's a lemma. This is not due to us, this is classical. So suppose the triangle 0, ZW has all angles less than or equal to 2 pi over 3. Then the point P is inside the triangle. And forms the tripod. A tripod by connecting P to the corners. That is, so here's the picture basically. Here's maybe Z, here's W, here's 0. This has all angles less than 2 pi over 3. Here's P. And there is this, so this P is kind of this tripod point. I'm going to tell you how to construct this point in just a second. Okay. So questions about the statement of the lemma?
I have a question.
Yes.
Does this lemma suggest that if a triangle has an angle greater than 2 pi over 3, then this point doesn't lie inside the triangle?
Yes. It's a good exercise to see where this I mean, it doesn't lie in the, this lies actually in the interior of the triangle. Honest to God, in the interior. So that's the crucial point. So think about a degenerate case, and then it's going to be kind of on the edge of the triangle. So it's a good exercise to do it with an angle of exactly 2 pi over 3. You could even do an isosceles with an angle of exactly 2 pi over 3 and 2 pi over 6s, and you can try and play with this, and you'll see that you're going to get something on the edge of the triangle then. Let me tell you the construction, how you actually get this point. This is a beautiful, this point is also called, P is also called the first Fermat point. Here's how you do it. So suppose you have your triangle, okay? What you do is on each edge, you draw an equilateral triangle. Okay. And then, this is a freehand drawing, of course. I have a better drawing, I can do a better drawing for you up here, and I'll do a better drawing for you in a minute. And then what you do is you connect the opposite vertices. So you connect that to that.
Jayadev, I think your screen might have just completely frozen now.
Great. Great, at the key moment. Let's try this again. Stop mirroring, and now let's start mirroring again. Okay, do you guys see it now?
Yes. Yes, it's arrived.
Excellent. So this is, the black triangle is my original triangle. On each edge, I draw an equilateral triangle. And then from each corner of the triangle, I draw a straight line to the opposite corner of the equilateral triangle. Just like in this picture, hey, it worked. All these lines all meet at a point. That point is the tripod point P. And this, and if I can get rid of some of this extraneous stuff, this stuff is the tripod. What I'm going to leave here is the tripod. If I can do it, actually I need to make my eraser smaller. There we go. So let's do P in black here, and then this. Right. So this little thing is the tripod. This is a really gorgeous construction. It's not very hard to prove. I think it's not so easy to come up with, but it's not very hard to prove. Now, in general, solving these kinds of combinatorial optimization problems, saying, or these kind of geometric optimization problems, saying, oh, you give me some collection of points, find the point which minimizes the sum of the distances, or maybe the sum of the distances squared. These are very hard computational problems. In the case of 3 points, you can actually solve it, and here's your explicit algorithm. And in fact, let's actually be a little bit clear here. So if this point is z, and this point is w, and this point is 0, these points can all have and then the other thing is the length of the tripod is equal to the length of any one of these segments. So either the blue segment, the green segment, and the red segment all have the same length, and it's all equal to the length of the tripod. That's also a really beautiful thing. Would you like me to write that down, or did everybody kind of get that, what I just said? These blue, green, and red lines all have the same length, and they're also equal to, if I add up P minus W, P minus Z, and P. Absolutely. So what we're saying here, so what is this point? This point is actually, you can write it in a couple of different ways. It's W plus, well, now this is Z minus W times e to the 2 pi I, sorry, e to the pi I over 3, not 2 pi I, e to the pi I over 3. And it's also, so you can, and this point is Z e to the minus I pi over 3. It's rotated 60 degrees down. This point is W e to the I pi over 3. And the point is all of these, so the claim is that all of these things have actually the same length. Z minus e to the I pi over 3 W is equal to W minus Z e to the minus pi over 3. That's very easy to see that these two things have the same length, because one is a multiple of the other by e to the I pi over 3. And then that's also the same thing as just the length of this. The fact that these three all have the same length and that these are all actually equal to Z minus P plus W minus P is a really, this is not so hard to prove. This is a check, a kind of a Euclidean check. Okay, so now I want to try and say, how do we go from this to setting up our counting problem? So now our counting problem, so what we're going to do is we're going to say, well, we lift our thing up here to have a tripod. So we lift our tripod so if we want to say, suppose we have a pair of vectors ZW in Z adjoined I squared. First of all, what we'll want, so maybe Z is sort of M plus Ni, and W is maybe K plus Li. For this thing not to be really a multiple of everything, we'll want GCD of Mn KL to equal 1. That's the kind of primitivity condition. We can also say that we want, so we don't count things too many times. What we're going to do is we're going to move the largest angle of the triangle to 0. So we want the triangle 0ZW to have largest angle at 0. Otherwise, you could keep, sort of moving things around. So we're going to nail this down without ambiguity. You might say, oh, there might be triangles which have two largest angles. That's going to be kind of a lower order contribution to the count. And we want all angles less than or equal to 2 pi over 3. And now we have this beautiful length formula. We have Z minus e to the I pi over 3W, or W minus Z e to the minus I pi over 3. All of these things, and we want this kind of length, Z minus, I could write it like this, W I pi over 3. Yeah. to be less than or equal to r. That's what we're asking for. This is now our counting problem. We're trying to count things in z of joint I quantity squared. We want the largest angle to be here. All angles of the triangle to be less than or equal to 2 pi over 3. In particular, we just need the largest angle to be less than or equal to 2 pi over 3, right? If the largest angle is less than or equal to 2 pi over 3, all angles are less than or equal to 2 pi over 3. And z minus w e to the I pi over 3 less than or equal to r. I'm going to rewrite this a little bit in just a second. So let me carefully write down what our actual accounting problem is now. Okay. So, by the way, another way to rewrite this, you can rewrite this as I'm going to rewrite this as z e to the pi over 3 plus w e to the minus I pi over 3. That's yet another way of writing it. And that's just going to help us a little bit in the way I've set it up. Okay. So our counting problem, n of r now becomes the number of zw in, well, really, it's going to be now a counting problem in z4, because z adjoined I squared is the same as z4, so that, sort of GCD of all the entries is 1. So if z is equal to, I think I said m plus ni, w is equal to k plus li, I want GCD of mn kl is equal to 1. I'm going to stop kind of writing this in a minute, but then we want this largest angle at 0, and that should be less than or equal to 2 pi over 3. And we want this length quantity, z e to the I pi over 3 plus w e to the minus I pi over 3 to be less than or equal to r. Okay. Notice, though, this is a thing that's kind of invariant under scaling, right? Like, or let me put it this way: if I scaled z and w by t, every quantity here, the angles don't change, and this counting problem, this length quantity also just scales by t. This is the length of the tripod. So if I call the tripod of zw, this is sort of the length of the tripod of zw. So the claim is, so first of all, we're going to have to write down, so I claim that actually this thing is going to be asymptotic to the following thing: 1 over zeta of 4, r to the power 4, times the 4-dimensional volume of sort of zw in sort of, or maybe I'll call it zeta omega in C2, where we have these same conditions. We have this largest angle, all of these conditions just about zeta and omega, except now we want the length, zeta e to the pi over I pi over 3 plus w e to the minus I pi over 3 is less than or equal to 1. So here's the general principle. If you have a nice set in Rn, and you want to count primitive lattice points in a dilate of that set, the asymptotics for that are 1 over zeta of n, r to the n, times the volume of the set itself. So that's what we're doing here. This is a dilate. We're counting primitive integer points in the R dilate of this set, where we ask for this length to be less than or equal to 1, and we have, of course, these angle conditions. This largest angle condition, angle at 0 and less than or equal to 2 pi over 3. So now what I want to do is I want to write down this angle condition, and I want to give you some indication of how you actually compute this volume. Okay.
Sorry, can I interrupt?
Please.
Could you repeat the last principle that you said? And is that really a theorem, or?
Yeah, it's okay. So it's a theorem if you add some conditions. So the last principle that I said is, and maybe I'll just write it down here. Suppose you have a subset A in Rn. Let's say it has piecewise smooth boundary. You can actually do much better than this. You could just say piecewise C1, but let's just say piecewise smooth boundary. Then suppose you want to count the number of things, primitive integer vectors, in, let's say, a scaled version of A. That's asymptotic to 1 over zeta of n, t to the n, times the volume of A.
Yeah, thank you.
So,
and is it easy to find references for this?
Actually, it's funny. I was just writing to a friend who does lattice point counting, because I never know how to historically properly cite this, because all lattice point counting people are like, oh, this is just Mobius inversion. Once you do the full lattice point counting problem, if you say you don't insist on primitive, then you get this kind of, you get without this 1 over zeta of n. And then to make it into this, get a 1 over zeta of n out front, you get, you use Mobius inversion. I think there's a paper of my friend Igor Vigman in which he writes this down kind of carefully and sort of more generality, but yeah.
Thank you.
Yeah. It's actually not so easy to find the kind of correct reference for this, if that makes sense. I don't know who first wrote something like this down. But the general point of view, and this has been used by many people in my business, is you have some nice, even piecewise linear structure on a space. You want to count integer points. The number of integer points should be kind of proportional to volume times scaling factor. Okay, so now the question is, here's a region now. We have a region, omega, is zeta omega in C2, such that the triangle 0, zeta, omega has its largest angle at 0, and that angle is less than or equal to 2 pi over 3, and zeta e to the pi I over 3 plus omega e to the minus I pi over 3 is less than or equal to 1. Okay. And so our goal is now to try and compute the volume of omega. Okay. First of all, what does it mean that we want the largest angle to be at 0 and to be bigger than or equal to 2 pi over 3? Well, first of all, the largest angle is opposite of a triangle. The largest angle is opposite the largest
side.
So the first condition is we just need that zeta minus omega is bigger than or equal to zeta or bigger than or equal to and omega, right? That means the largest angle is at 0. The law of cosines tells you that, okay, so remember the cosine of 2 pi over 3 is -1/2. And cosine is decreasing on 0 pi, right? All deep calculus or deep trig facts. So if we want to, and remember, how do we compute the angle? Well, okay, so we have that zeta minus omega squared is equal to zeta squared plus omega squared plus 2 zeta omega cosine of this angle theta between them. So cosine of theta, in other words, is equal to zeta minus omega squared minus zeta squared minus omega squared over 2 zeta omega, and we want this thing to be bigger than or equal to -1/2. Right, that's all we want. So now we plug this in, you do a little algebra. So now what do you want out of this? It boils down to you want zeta minus omega squared to be, bigger than or equal to, we multiply both sides by this denominator, so we have a minus zeta omega here, plus zeta squared plus omega squared. Did I get that right? No, I think I got, I think I did something wrong here.
So I believe the law of cosine has a -2 instead of a +2.
Thank you. Thank you. Thank God for that. So this is divided by, now we flip this, right? So we want to divide by this, that's negative cosine theta. Right, so now if I can do division on the fly, divided by -2, we still want this to be bigger than or equal to -1/2. Yes, that's fine. So now when we multiply out by this -2 zeta omega, that becomes a plus zeta omega over here. And we have to flip the sign of the inequality because we multiplied by a negative. And so we get this here, right? So what we want, so our set omega now becomes the following: zeta omega in C2, so that zeta minus omega squared is bigger than zeta squared and omega squared, but zeta minus omega squared, sorry, my writing is getting worse and worse, so my zetas look more and more like rows, is less than or equal to zeta omega plus zeta squared plus omega squared. Okay, and we want zeta e to the I pi over 3 plus omega e to the minus I pi over 3 to be less than or equal to 1. Okay, so this is the set we need to compute the volume of. And I guess the key lemma here is that the volume of the set is what I said it was, is the volume of the set omega is, what do I want to say it is? I said at the beginning, the theorem said sort of 15 pi over, yeah. So the claim is the volume of omega, let's call this omega tripod. The volume of omega tripod is square root of 3 over 48 times 2 pi. It's square root of 3 over 24 times pi. Okay. So let me give you a very brief sketch about how we compute this volume, because I'm actually quite proud that I was able to compute the volume of a region in R4. Here's the key idea. Actually, I'm going to go to some pre-written stuff here because I want to go a little bit more quickly, if that's okay with you guys, because we're running short on time. Here we go, tripods. Yes, very good. We have some nice pictures here. Okay. Right, so this is a brief recap of what I said. You know, this is theta less than or equal to 2 pi over 3. This is our tripod region. So we want to end up computing the volume of this region, omega super tripod. And what we're going to do is we're going to fiber it. We're going to fix the first coordinate and consider the set of omega in the fiber over zeta. That is, the set omega tripod sub zeta is the set of omega satisfying these conditions. Notice I claim that the volume of the set only depends on actually the absolute value of zeta. You know, it doesn't matter if you rotated zeta, this whole set would just rotate with it. It's a question in the chat. Oh, that was before, Karthik, yes. That was, yeah, the law of cosines, there's a sign error. Yes, thank you. Okay. So now we might as well take, let's just take like zeta to be real. Okay. So let's take zeta to be real and let's say S positive, to be positive. So notice this is what I wrote down, is that this thing kind of varies equivariantly by multiplying by e to the I theta. So first of all, we need zeta minus omega to be bigger than or equal to zeta, which means omega is outside of this green circle. Omega has to be outside of this green circle because it has to be, zeta minus omega has to be bigger than zeta. So omega has to be more than distance S away from the point S. Also, the other condition I didn't say is I want zeta to omega to be kind of positively oriented. So I want the angle to be less than 2 pi over 3. So, and I want it to be kind of positively oriented. So zeta should be omega should be between the x-axis and the line and the ray, the pink ray, t e to the 2 pi I over 3. Okay. Now, if you write down zeta minus omega being bigger than omega, say omega is x plus iy, you write this down and you get that omega, actually the real part has to be less than or equal to s over 2. So you have to be kind of to the left of this vertical yellow line. Finally, if you want zeta e to the I pi over 3, remember that's also the same as omega plus z times e to the 2 pi I over 3. I need that to be less than or equal to 1. In other words, I need omega minus s e to the minus I pi over 3 to be less than or equal to 1. This is just rewriting that condition. So I need to be inside this kind of peach circle. So I need to be inside the peach circle, outside the green circle, in between the electric blue and pink lines, and to the left of the yellow line. In this case, there's actually nothing. For this particular S that I drew, there's actually nothing in the fiber. Okay, so here's some claims about this set. This set is actually empty as soon as S is bigger than 1. Okay. The region actually changes shape a little bit at S is equal to 1 over square root of 3. This is when some of these curves end up intersecting. And actually, let me show you this is a hand-drawn picture of a region. This is the region S is equal to 1/2. This is the region of possible omegas. It's again outside the green circle, to the left of the yellow, to the right of the pink, to the left of the electric blue, and inside the orange circle.
Your screen might have frozen again.
No, such a beautiful picture that you're missing. Actually, you know what? I'm going to share a different screen with you. Hold on. New share. Can you guys see this now? But this is
Yes.
I'm way ahead now. Okay, let me go back now to there's the hand-drawn picture. Okay. Here is a better Desmos drawn picture of the region. This is S is equal to about a third. This is S still less than 1 over square root of 3. It's this kind of 2 circular arcs and 2 straight lines. Okay. Here's what happens after you cross 1 over square root of 3. The region changes shape to this kind of 2 circular arcs and 1 line segment. As S gets closer and closer to 1, the region gets really, really tiny. So you can see the region is getting kind of smaller and smaller, and at S equals 1, the region just degenerates to a point. It has no volume. Let V of S be the volume of this region. Then, of course, volume of omega lambda, omega tripod, is, well, you integrate over, well, I'm saying integrate over all zetas, but that's just integrating S, you know, and then multiplying by e to the I theta, so that's S ds d theta. So if I compute this V of S, I'm in business. I can compute the integral of this V of S, and then I'm done. So how first do I need to set up the computation of this region volume omega S? And for S less than 1 over square root of 3, it's very easy to set up. The key insight, though, is going back to here, the key insight in setting up these integrals is you don't use polar coordinates centered at the origin. You use polar coordinates centered at this point, e to the minus I pi over 3s. And you use them with this line, with this particular line as your x-axis. This orange line is kind of your x-axis. Actually, yeah. That's not quite true. I lied a little bit. So let me actually make this remark. The key of this proof is use the polar coordinate space that AC to the minus theta over 3 with theta equals 0 is being the line passing through S. Sorry, it's the line going from e to the minus I pi over 3s to S. We use that as our kind of 0 line, theta equals 0 line for polar coordinates. Then this vertical line becomes the line theta equals pi over 6. This line becomes the line theta equals pi over 3, which is what's showing up in these pi over 6 and pi over 3. And then this is just setting up the integrals. And if you set it up properly, so you get, for one region, it's pi over 12, 1 minus 2s squared. For the other region, it's a little bit more complicated. So here you can see the explanation. This is the theta equals 0 line. This is theta equals pi over 6. This circle is theta equals cosine theta. The circle is r is equal to 2s cosine theta in these coordinates. And this theta, when we hit the circle, is cosine theta, cosine inverse of 1 over 2s, which give you the limits of integration here. And if theta is less, if s is less than 1 over root 3, 2s cosine theta is less than pi over 6, and so you go from pi over 6 to pi over 3. That's your range of integration. And now you compute your V of s's, and you actually end up getting, this is, you get your V of s is basically integral from max of cosine inverse of 1 over 2s pi over 6 to pi over 3 of this slightly irritating looking integral. At s equals 1 over square root of 3, they actually coincide. We're now going to compute these integrals. When you compute them, this is what you get. This is what V of s is. Looks kind of horrifying. But now we have to integrate V of s. So this is the proof. This is just, you write it down, you compute, you do some checking. I'm happy to share these notes with people. And now what you do is you break up V of s into two. So now we want to compute volume of omega lambda, which is the integral of s V of s, 2 pi integral of s V of s ds. Now you break it up into two pieces. First is the piece from 0 to 1 over root 3, because we understand the shape much nicer there, and that gives you a pi over 108. The second piece is where V of s gets much more complicated. It has these cosine inverses and s squareds and square roots. We're going to break that up into 4 pieces. This integral pi s over 3, this other crazy integral, this other integral, and 1, 2, 3, and 4. 1, 2, and 4 I was able to do by, 1, 3, and 4 I was able to do by hand. 2, I had to ask for help. I did what our good calculus students do, and I asked Wolfram Alpha. And lo and behold, Wolfram alpha spit out a beautiful answer. The answer for that definite integral is 7 square root of 3 plus 4 pi, with 1 over 432 out front. Okay, so now we have to add up 0 plus 1 plus 2 plus 3 plus 4, or a plus 1 plus 2 plus 3 plus 4. So now we add these all up, and here's something kind of miraculous happen. These integrals have things with pi's in them and with square roots of 3's in them. They're all in sort of q adjoin pi and square root of 3. What's remarkable is all the factors with pi end up disappearing. Only the factors with square root of 3 end up surviving, which gives you this square root of 3 over 48 and then the 2 pi out front, and gives you this volume of omega lambda is square root of 3 over 24 times pi. I actually spent that's what I spent most of my quarter doing, was computing this volume. And then you plug it into this formula that n lambda of n tripod of r is 1 over zeta of 4, volume of this tripod region r to the power 4, and you get this 15 square root of 3 over 4 pi cubed. So now, of course, the question is, what the hell is 15 square root of 3 over 4 pi cubed? How does this, what does this thing mean? And so, okay, that's email from a co-author. Maybe I stopped that there. So I think this might be actually a good place to stop, because I think I've essentially given you how to prove this as well. And so I would love to have questions on the context of this and what we want to do with it next. So just to seed that, I will point out that those are the questions I would really love to have. So I'll stop there. Thank you.
Okay, maybe before we get into the questions, let's thank Jayadev. So we should have reaction buttons or just clap. Okay, and any questions?
I'll bite. What does it mean?
Yeah, what does it mean? Okay, so this is a really great question. I don't know. So I would suspect my suspicion is this 15 square root of 3 over 4 pi cubed should be some ratio of volumes of spaces of differentials. Okay. Where does the problem come from? The problem comes from, suppose you think of dz quantity cubed as a cubic differential on the torus. Then these are sort of 3 lines shooting out that are kind of indistinguishable, right? These are all lines of sort of the real part of a cube root being 0, or imaginary part of a cube root being 0. This is an example, very simple example of just a web on a surface. So you shoot out, you have this this trivalent vertex, and you're shooting out things, and they're all ending at singular points. In this course of the study of spectral networks, Andy Knightsky has asked, so a spectral network is basically you have a graph on a surface associated with a list of differentials satisfying a certain polynomial equation. And one of the things you might want to do is you might want to count in the holomorphic case, at least, or the mirrormorphic finite area case, you might want to say, how many of these possibilities are there? How many ways can I draw these webs with trivalent vertices that where things are allowed only to terminate in singular points? So this was a problem we came to at MSRI. So we followed there's this advice of Polya's, which says, you have a problem, there's a simpler problem you can't solve. If there's a problem you can't solve, that was a problem. Andy's problem that he was posing to us was a problem we couldn't even really formulate properly. So we started by saying, okay, let's try and formulate it. David Alcina said, why don't we formulate it in a case we can actually understand? Why don't we say, let's look at the torus and let's look at a very simple trivalent graph, just this one trivalent vertex shooting out these 3 things and having the 3 things terminate in a marked point. Can you even count that? And so this is where we started. What we are hoping to do, and I think this is going to be a really long-term project, is that these kinds of things should be the analog of saddle connections for these lists of differentials that arise in higher Teichmuller theory. So I realize that's not a terribly satisfying answer, but that's because we also are trying to figure out what the right generalizations ought to be. Is that useful, Aaron?
It is, yeah, thanks. Quick question. You did say that you think they might be conjecturally, not even necessarily conjecturally, maybe they're ratios of volumes.
Yeah.
Are there natural notions of volumes for higher order?
There are not yet, but actually, okay, so there's a couple of, actually, yes, maybe I'll say one yes. So Dukman Nguyen defined an analog of Mazurvich volume for spaces of higher order differentials. And in fact, I believe even showed that it was finite for the settings he was considering. Now, more recently, Alexander Thomas just defended his thesis, and he is defining these ideas of what are called higher complex structures, he and Vladimir Fock, which are supposed to be kind of the uniformization analog of hyperbolic metrics for these, or rather, they're the, so you have complex structures and you have hyperbolic metrics in the classical setting. In the higher Teichmuller setting, you have these representations in the SLN, and what's the sort of the thing on the, that's kind of the geometric side. What do we have on the complex side? And they've proposed a definition for that, what they call higher complex structures, modeled on what they call, what's the name of the, there's a certain kind of, modeled on something called the Hilbert scheme. Now, in his thesis, it's not in the papers yet, but it's in his thesis, Alexander Thomas defines an SL2R action on the cotangent bundles of this space. The space also has natural period coordinates, and there should be an analogous construction of Mazur-Beach measure. And if I had to guess, I would guess that this number ought to be some volume of one of these spaces, or some ratio of volumes of a couple of these spaces. But I think, you know, that's what I like. This is a story that I mean, I'm guessing I'm going to spend the next 10 years of my life trying to figure out the story, and 10 years if I'm lucky.
Okay, thanks. And thanks for the references.
Yeah. And Aaron, feel free to write to me if you want these references as well. I can point them to you as well. I should also point out before I say is that not only is this proved, it's also correct. What do I mean by that is I wrote a computer program to compute the number of tripods using it, you know, it's not a very good computer program because it chokes at about r equals 40. 40 to the power 4 isn't huge, but it's doing too many computations. But the error term between the computer program and the conjectural value is in the 4th decimal place. And it's a 1 in the 4th decimal place. So I'm fairly confident about this theorem. Not only have I proved it, I actually think it's true.
All right, well, if there are no more questions, let's thank Jayadev again.
Bye, guys. Thanks for paying attention all the way through to the end and for sitting through painful integrals.
And so this was the last seminar this year for the UW Combinatoric seminar. We should be back again in September. We haven't got any more details yet, but yeah, check again in September. And yeah, thanks for everyone who came.